Let's continue the Seidel, the Gauss-Seidel power flow method. So the idea of a Gauss-Seidel method is very simple. You have a set of equation you want to solve. For our case, it is the power flow equation. So original equation may have everything on the left-hand side and right-hand side. We want them to be 0. First, you need to rewrite the equation to pick the variable to be calculated to the left, to move it to the left-hand side. So you need to rewrite the equation in this form, depending on which one you want to calculate. Then starting from here, you can iterate. You just give some initial estimate for those values. Then you just plug in the initial value to the right and calculate the left, and then you just repeat this process until the update on the value of the variable is less than the error tolerance. You stop there. For power flow equations, we have this equation, but depending on which one to be solved, we can transform the equation to this first one. The first one will be useful to calculate the voltage phasor at each pass. We can also rewrite the equation to make left-hand side to have P and Q. So you can use this equation to calculate Q in the real imaginary part and the P in the real part. Then depending on which type of bus you are going to calculate, so you can use the first equation to give you the voltage, magnitude, and angle to any PQ bus. Just angle only for PV bus. For PV bus, you also need Q from the second equation. And similarly for slack bus, you also need Q. And finally, the third equation will give you the P value for the slack bus. We went through a different type of buses, starting from PQ buses, which are low buses in general. So the voltage, magnitude, and angles unknown for those buses. We only just have this formula. You just start from initial gas, and then just start iterations. To start iteration, you can assume some initial estimate for the voltage phasors. If it's close to a slack bus, you can just use slack bus as the initial estimate. So typically, slack bus will have voltage magnitude around 1 and angle 0. 0 means we just use slack bus as a reference for the entire system. Since PQ bus mainly representing the low buses, so typically the voltage will be slightly lower than slack bus, and angle will be slightly less than slack bus. So if you want, you can make an initial estimate for each low bus to have voltage magnitude less than 1, slightly less than 1, and angle slightly negative. But definitely, if you want to always use this simple initial estimate, that's fine, unless you have a better estimate. So for PQ bus, for each PQ bus, that's just simple. For PV buses, we need to solve voltage, angle, and reactive power. So we need to utilize the two different equations. The first equation to calculate voltage phasor, but we take an angle value. Second equation to calculate compressed power, we take an imaginary part for Q. For each PV bus, we know P and the voltage magnitude, so those will be known. So we need to keep P and absolute V constant during the entire iteration process. For the initial estimate, we only need to assume an initial angle. If you don't have better knowledge about this angle, you can simply just take 0. But because PV buses usually mean generators, so generators will generate IT power. So in order to deliver IT power, from those generator to neighboring low buses, usually the angle need to be higher, right? So if we use slide bus as a reference, which means average angle for the entire system, usually PV buses will have angle slightly positive. So if you want, you can start from a small positive number, but if you like 0, that's also fine. That may just increase the iterations. So we'll need both formula. The first formula calculate the Q from the compressed power. The second formula calculate V. Okay. So we don't call this one to be the voltage phasor because we don't utilize the entire phasor for our next iteration. Why? Because for such PV bus, the magnitude already determined. We cannot change that magnitude during this process. So if you calculate this, the updated voltage phasor for this PV bus, and if you calculate absolute value, that may be different from the absolute value given by the equation, by the problem. So which means we cannot utilize this phasor completely. What we can do is we keep the absolute value unchanged, but we only update angle. So how do we do that? One way is you can definitely solve the angle. If you want, you can solve the angle. Oh, let's see. So which means you calculate the absolute, we call it the VCI, right? K plus 1 iteration. Then we give it angle. Okay, if you want, you can calculate the absolute value and angle. And this angle is fine. You can take this angle, but this magnitude will be replaced by the absolute value given by the problem. This is one way to do it. If you calculate this polar form, which is easier to you can take this approach. But sometimes when you calculate the complex number, the calculation usually give you a real part and imaginary part separately. Okay, to avoid additional computation to find the angle and the magnitude, we can pick either the imaginary part or real part to update and keep the other one calculated based on the absolute value. Okay, because the real part, imaginary part, the two numbers only have just one to be free to change. The other will be dependent because we have the constraints saying the absolute is constant. Okay, so if you calculate the calculation, direct calculate the real imaginary part. So the textbook suggests the method, which is you keep a imaginary part unchanged. Then you keep the imaginary part from that answer, and the real part will be calculated based on the absolute value. Okay. Then you can ensure the new voltage phasor have to have the same absolute value given by the problem. Okay. So this is just a figure showing what happened during this process. So you calculated this the new voltage phasor, which has a longer absolute value, longer magnitude compared to VI. So you only keep the imaginary part, and for the which is you keep this imaginary part, but for the real part, that is calculated based on the magnitude. So to ensure the updated phasor stay on the same circle, okay, for the same radius equal to the absolute value. So you just continue this process until the update is less than the error tolerance. If you want to utilize acceleration factor, as acceleration factor can be added here, you can introduce alpha. So if you want to accelerate this process, which means you take larger steps to update the value, which can be visualized as taking a larger stairs to climb up until you convert to a solution. So alpha usually need to be bigger than 1. In some algorithm, if you find it's very hard to convert, and sometimes you can adjust alpha. You can maybe at the beginning use a bigger alpha, but later you reduce alpha to give you a fine adjustment near the solution. Yeah, so alpha it just give you additional dimension to control the speed of the performance of the method. So that's what we need to know about the PV buses. So lastly, the slide bus is very simple because slide bus simply just calculate the P and Q using all the values already know about the rest of the system. So when we calculate slide bus, we already know the voltage phasor everywhere. Since for PQ buses, we calculate the voltage phasor. For PV buses, we calculate voltage angle. So eventually we have everything when we want to calculate slide bus. So basically you don't need to involve slide bus during iteration. You just iterate on PQ buses, PV buses, and when you calculate all the voltage phasor, you just in the last step calculate slide bus. So slide bus just try to determine the P and Q to maintain the power balance of the entire system. Okay, so the last step is just to calculate a current based on the Kirchhoff current law. So once you know the current, that will be the current injection to each bus, which is equal to the current going to the local admittance to the ground, and also another current is connecting this bus to a neighboring bus. So since you already know admittance, we know voltage phasor on both ends, so we can calculate both current. So we need to calculate current injection from each bus because even for the same transmission line, the current injection from two terminals can be different, right? Because there's a component of the current going to the ground from each side. So once you calculate the current from the both side of the transmission line, you can calculate the compressed power. So here we define the direction of the current be from the both side to coming to the middle of the line. So which means if you add those two a compressed power flow, so that will give you the power loss. So it's like the power loss is supported by the compressed power from both sides. Okay, so then we have everything we need for the power flow problem. So we calculate the voltage phasor using the for the PQ buses, angle and Q for PV buses. And at the end, we calculate the slide bus P and Q to balance the entire system. Then we know the voltage phasors, we can calculate current injection. Using current injection, we can calculate compressed power. Then finally, we can calculate the loss. Any question? All right, so next of the lecture, I'm going to utilize two examples from the textbook to explain the detailed step to calculate the power flows. So I only talk about the important information step from those examples. So please read those two examples after the class. So in the first week of November, I will be out of town. So I have the JTA, my PhD student, to go through those examples again, because the textbook has a toolbox with MATLAB code to help you to solve the power flow based on some functions provided. So I will let the JTAs, the PhD student, go through those examples. So if you bring your computer to the class, so you can just go through those the toolbox step by step. So that can be very useful for your final course project. So the second project will be about the power system planning study. Okay, let's talk about the example 6.7. This is a toy system with only 3 buses, but it is a power network, literally speaking. So here we assume we have a one slide bus, which is bus 1. So you see for slide bus, we gave a voltage 1.05. So this slide bus may mean equivalent generator representing a large system. We use the angle of the slide bus as a reference, so which means we know the both magnitude and angle for this bus, but we need to solve P and Q. We need to solve P1, Q1. And the other two buses are both PQ buses. So we give them P and Q at each bus, and we need to solve voltage, magnitude, and angle. Okay. And this system is very simple. Any two buses connected by a single impedance. So which means it can be a short line, ignoring the admittance to the ground. So that make a construction of the bus admittance matrix easier. Okay, so we want to use Gauss-Seidel method to find a power flow solution. And we put the error tolerance equal to 0.0001, which means we want to make sure the full decimal places to be accurate. Okay, so to summarize what to calculate, we want to solve P and Q for bus 1, and the voltage, magnitude, angle for bus 2 and bus 3, and then the line flow and also the loss of line. First step, let's check what I know, because we want to iterate. We want to make sure in the iteration equation, we have first some variable which already know, so which we will keep a constant. For example, the P and Q for the PQ buses, they will stay at constant without any update. And the second type of variable will be the variable to be solved, such as voltage, magnitude, and angle. But at each iteration, we start from the initial guess and we plug in that value. And we just assume those values to be temporary node, but we need to update in the next iteration. Okay, so let's figure out what I already know. First is we know the impedance of each line. We simply just calculate the reciprocal value, which will give you admittance of each line. Okay, so we put those admittance there. For this case, the bus admittance matrix will be symmetric because there's no phase shifting. It will be very simple, 3 by 3 matrix. So next, since we know P and Q for each PQ bus, so we need to translate those values into per unit. We have 100 MVA as the power base. So 100. So we divide each number by 100. And because here, when we call the compressed power injection to each bus, we assume the direction will be from the external to the network. So for PQ buses, so if they represent actually the load, which means their P and Q will be negative. Okay, so here I indicated just the direction will be the power leaving from the network. But when you construct the compressed power for each bus, you need to add a negative sign. So first you divide each number by 100. So you'll calculate, get the compressed power for bus 2 and bus 3. But please pay attention to the negative sign here, which means they are negative injections, not positive injections. So those numbers will keep a constant in the iteration. Okay. So let's move on. Okay, so I already colored those numbers in black. So those will be the constant value. So because this problem only have 2 PQ buses, so each PQ bus only need this formula to calculate voltage phasor. Okay, so here something I have to explain. Because you have 2 PQ buses, but if you calculate for much bigger system, you may have thousands of PQ buses. So only this formula is useful for PQ buses. depend on how you want to calculate. If you want to do the calculation in parallel, which means you have many processors or many threads which can compute this equation together. So they can be so such calculation can happen concurrently, which means at each iteration you plug in the value, right, from the previous iteration. Then you have the new value. So this finish one stage, one step. Then you plug in those value to the right-hand side, and you go to the second iteration. That's completely fine. That's a default setup for this Gauss-Seidel method. But if you do the calculation by hand, sequentially, not in parallel. So when you calculate the case iteration, you get the case value, right? So then you get the k+1 iteration, the value, the new value. Okay. So when you calculate, for instance, the VI at k+1 iteration, the I may be, for instance, like a bus rate. So you want to calculate bus rate voltage at k+1 iteration. But at this moment, the bus 2 voltage already available, right? Because you calculate bus 2, then bus rate. So here, it's okay. You can take the latest value of bus 2, if that you believe that is more accurate. So basically, the idea is here. So when you plug in those values, you take whatever available, which is more accurate. So if you have either the value you just calculated at this iteration or the value from the previous iteration, so you believe the latest iteration is more accurate, then you take that value. But you don't have to. But the textbook assume you always take the most accurate value. Let me explain what happened on this example. So we start from an initial estimate, right? For bus 2, we just simply assume 1. And bus 3 is just 1. Okay. That's iteration 0. Then we go to iteration 1. So we use the same formula twice, right? For first for bus 2, then for bus 3. So we calculate the bus 2. We plug in. Here is just the initial estimate for bus 3. And here is just initial estimate for bus 2. And then we get this value. So this value is actually the result after the iteration 1 for bus 2. Then we move to the bus 3. So based on the default setup, we should utilize this initial estimate, right, for the bus 3. And here we also use initial estimate for bus 2. So that's what the what is planned for the original default method for Gauss-Seidel method. So if you want to do a parallel implementation, but since we already have this better value for bus 2, we don't take that initial estimate. Instead, we take this better estimate. So that will make you iteration faster to convert to the final solution. So either strategy is fine. But if you want to do a calculation by hand to get the solution sooner, you can choose the more accurate one. Any question here? All right, so let's continue on. Then the second iteration, it will give you new value. Third, so you continue in the textbook. For this example, it took up 7 iterations. Then you see that there's basically no update because if you compare the first decimal after the first digit after decimal, they're basically the same. Okay, so if you do further iteration, there's not much, there's no update. Okay, so we can stop here. So we will pick those value as a voltage phasor. You can convert the value into the polar form to give you absolute value and angle. So you see those angles are slightly negative, right? Compared to 0 angle of the slide bus. So that makes sense because you want to deliver the power from IT power from the slide bus to the two load buses. So they need to have slightly negative angle to receive the power, IT power. Another observation is because both PQ bus consume ready power, so their voltage also slightly lower than the slide bus. Right? In order to receive ready power, you need to create the gradient of voltage. In order to receive the IT power, real power, you need to create the gradient in angle. Okay. All right, so that's done. That's a example. This example. It's very simple. Okay, yeah, we have the last step is just calculate the slide bus. If we have all the voltage phasors, we just calculate slide bus power, then translate it back to the P and Q in megawatt and megavar. Finally, we calculate the line currents. For this case, there's no admittance for the ground, so the current injection from each terminal of the line will be opposite to the current of the other one. So we only just need to calculate, for instance, I12, I13, and I23, and the other one will be simply just take a negative value. Finally, we can calculate compressed power and the loss. So those values are already marked on this network. So on each terminal, the first number is P, the number under the line is a Q, and the number on the line will indicate the loss of the P and Q. So this is done. Example 6.8, which is about the same, pretty much the same system, but we make one change. We change the bus rate to be a PV bus from a PQ bus. Bus 1 is still a slide bus. So for the PV bus, we assume the voltage magnitude to be 1.04. So the angle and the compressed angle and ready power will be calculated. And P is given at the 200 megawatt, which is like scheduled generation for this power plant. Still, the first step is to check what I already know. Okay. So we have for the bus 2, we have a P and a Q, and we can change those numbers to the per unit values, and so don't miss those negative signs because that's a power leaving from this bus. For bus 3, we only know P, okay? So that is a 2.0. This is positive because bus 3 has real power injection to the network. So that number is a positive 2. Step number 2, we need to iterate on both the PQ bus and PV bus. So we'll need to use both formulas here. The first formula for the PQ bus and the PV bus, the second formula for the PV bus. We start some the iteration from an initial estimate. Okay, for bus 2, we know nothing about the voltage. We just simply assume it to be a 1.0 with magnitude of 1 and angle 0. For bus 3, we already know the magnitude, but we don't know angle. We simply just assume the angle to be 0, right? Okay. All right, so from the first formula, we just plug in those initial estimate. Then we can get the voltage phasor for bus 2. Then for the ready power of bus 3, we just simply use this formula, Okay, so you see here, it also utilizes a more accurate one instead of the initial estimate. This is just an alternative strategy. If you want to use V2, the initial estimate, that's also fine. But since this value is more accurate than the initial value, so we just take the more accurate value. All right, so next we iterate for the bus 3 voltage. So we take this Q to be plugged into the right-hand side of the second formula or the first formula. Then also the more accurate estimate about the bus 2. Then we have the voltage phasor on bus 3. We cannot just use this value at the whole phasor for the bus 3 because it may change the absolute value. So if you check the absolute value, it is 1.0378. It's different. It's different from the magnitude we gave for the bus 3. So here we only just take an imaginary part. And for the real part, we will calculate from the magnitude. Okay, so we use the imaginary part and the calculated real part and to form the phasor for the bus 3. So this one will have the absolute value 1.04, same as the voltage of the PV bus. So by now, we only just finished the first iteration. You need to continue this process until the update is less than the tolerance. So on this slide, I just summarize the result from the other iterations. So those are the value from the previous slides after the first iteration. And in the 2 columns, we're going to iterate for bus 2 and bus 3. So I marked how the value is actually updated on those formula. So if we continue iteration 2, then after 7th iteration, we see the update is actually happen only at the 5th digit of the decimal. So which means we can stop here. So the error tolerance is less than 0.0001. All right, so we can summarize the final answer. For voltage at bus 2, we can simply take this value. We just need to translate this value to the polar form. Okay. Bus 3, we can simply take this value. But for Q3, so this Q3 is actually calculated from the previous iteration. Since we already have the more accurate V2 and V3 after 7th iteration, we'll do one further step of update by using this formula again. So we just need to plug in the more accurate V2 and the V3 at iteration 7, then to update. So you see there's a little change after the third digit. Okay, so those will be the final answers for the system. All right, so the last step will be just to calculate the slide bus, then the current, continuous power flow, loss, and those numbers are marked on the figure. Okay, so we finish the Gauss-Seidel method. Any question? Right. So you can practice this method by the homework problem. Next, we can move to another method, which is Newton-Raphson method. So let's talk about this method. Compared to a Gauss-Seidel method, the Newton-Raphson method is based on a linear approximation. A linear approximation, which means if you want to solve nonlinear equations within nonlinear functions, you can do a Taylor expansion on those functions, and you only just keep the first order term, the linear term, and ignore the other terms. It's still a measure based on iteration, which means you need to give an initial estimate for the solution. So let's just assume this is a general function. Okay, we have a nonlinear function. We hope this one to be equal to c. C is just constant value. Definitely you can move the c to the left and the right will be 0. Yeah, we just use this one. Okay, so the fx can be approximated based on the Taylor series expansion. So I assume everybody is familiar with Taylor expansion. So you give an initial estimate. Okay, so as then the actual x will be initial estimate plus some update, some deviation, some change. So Taylor expansion says this one can be approximated by the value, the function value taken at the initial estimate. Then there's a linear term. There's another term, second order term, depending on the second order derivative. And you just keep doing that. Finally, it will approach or converge to the true value of the function. So here I put this symbol in the parentheses. That's a derivative up to of the certain order. So on the superscript, I put the parentheses 0. This just simply means I'm taking the value of the derivative at the value at that iteration. So which means if I write anything like this one, this basically just means taking the derivative of this function, the first order derivative at case, the value after the case iteration. Okay, that's a notation I'm going to utilize for the rest of this section for Newton-Raphson approach. The Newton-Raphson approach just simply ignore any nonlinear term. They only just keep the linear part because it's based on linear approximation. So which means the gap between the c, the value of the function, and the estimate of the function based on some initial guess can be approximated by this linear form, which is equal to the first order derivative taking value at that initial estimate multiplied by some update of that s value. Okay, so this suggests an iteration formula, which means if I know the gap of the function value, and also know the value of the first order derivative at this initial guess, we can estimate how much we need to update this initial guess to give you a linear approximation. Then we can generalize this formula for any iteration, like up to case iteration. So at case step, if I have a better estimate, which is sk, even this one, it can be very close to the true value of s, but it still need to be adjusted. I can use this formula to adjust this value. So the update on this s value can be determined based on the current gap of the function value divided by the first order derivative taking the value at this x. Okay, so this will be our iteration formula. So the algorithm of a Newton-Raphson approach will be the following. So we start from the iteration 1 and we continue until the case iteration or k+1 iteration. until the gap, the change on the x value is less than the error tolerance. So the iteration formula will be, if right now we'll add the k+1 iteration, we already have the value from the previous iteration at iteration k. And so we need to update this value by this delta sk. The delta sk is calculated based on that formula. We have the gap of the function divided by the derivative taking the value at the sk. Okay, so if we compare this iteration formula to Gauss-Seidel method, so in the Gauss-Seidel method formula, we didn't use any derivative at all. So Gauss-Seidel method does not use any differential term. The differential term just give you the slope of how the function may change. So if you start from some initial guess, based on the slope, you can guess in which direction you can convert to the true solution. But Gauss-Seidel method doesn't use any differential information. So basically, the Newton-Raphson method approximates the nonlinear functions iteratively using a series of tangent lines at each updated value of x. So tangent line will have similar formula. So you can easily prove from the iteration formula at each step, it actually uses this straight line function with this slope and taking the value at sk to draw a straight line to approximate the curve at that step. That gave you a better visualization on what was happening during this process. We use one example from the textbook. That is basically the same equations we solved using the Gauss-Seidel method, right? When we solve this one using Gauss-Seidel method, we just move 9s to the left and divide both sides by 9. Then we start iterate. Okay, so here we are going to use a different formula involving the first order derivative. So in this plot, so we draw this nonlinear function as this black curve. In this case, C is just a 0. So C is just a line, a straight line, taking the value of 0. So the roots of the equation will be the first one, the tangent point, which corresponds to equal roots. And this intersection points correspond to just single root, right? We already know the root will be either 1 or 4. So what happened by the Newton-Raphson approach is just we start from, let's say, any initial guess. We just take maybe 6.0. So we're going to draw a straight line tangent to this starting point. So we'll go to a new point. Then we go up and draw another tangent line. Only after 2 iterations, you have been very close to the root at 4.0. Okay, let's do the calculation to give you more details on what's happening here. The first order derivative of this nonlinear function will be a quadratic function. So if we start from a 6.0 at the initial guess of x, so the derivative at the initial guess will be 45. 45 means this slope. This slope is 45. So we draw a line, a straight line with a 45 slope, tangent to this initial guess. So that can quickly move to another guess, a new value. That is this straight line. Let me clean up a little bit. So it will draw this straight line. Okay, so based on this straight line, they use this straight line to approximate that curve, but you can compare the value to the curve. It will tell you there's a gap. There's this gap. This gap is, the gap is 50. So the first one, the gap is 50, negative 50. Then you draw this straight line. Then you tell you the x need to be updated by negative 1.1, which means you need to move to the left by 1.1. So we'll give you a second guess of the value. All right. And by second guess of value, the x will be around 4.8. And the new gap will become much smaller. The new gap will become this one. And you just keep doing this one. Keep drawing the straight line tangent to the latest updated value. And after only 4 or 5 iterations, you already get to that root. So this one is much faster than Gauss-Seidel method. It also have the each root also has a domain abstraction, which means if you start the initial guess from the red zone, it will always convert to the 4.0. If you start from the blue zone, always convert to a 1.0. If you compare this figure to the original figure based on the Gauss-Seidel method, the Gauss-Seidel method start from an initial guess and will draw the zigzag shape of curves until converging to one of the root. But that zigzag shape doesn't utilize any slope of the curve. The Newton-Raphson approach also draw the similar curve, but each time it will just utilize the local slope information, right? So that can convert much faster. All right, so I stop here and we'll continue on Monday. So we talk about how to utilize Newton-Raphson for power flow.